All right. Okay. So today we're just going to do some example tutorial, maybe around 3 questions. Okay, we're going to do it together. Okay. So it's the same slides chapter, just that I have modified and add a bit extra questions. But it's okay. I will upload it after our class. So let's look at this one. I'm not sure this one have we tried it or not, because it's already in the slides before. So we'll see this one. Okay, so this one is about steam turbine. Okay, steam turbine. So we have to apply the first law of thermodynamics to calculate the magnitude of each of the energy by using the energy balance. Of course, first law of thermodynamics is always energy about concerning energy balance. Okay, so you're going to calculate the kinetic energy, potential energy, enthalpy, work done, and the mass flow rate. Okay, because we know the power is given here, the power output of the steam turbine. Okay, so so let me just start. We use the whiteboard. I need to draw a bit so that you can understand. The link sharing on, and the link and view. Okay, change. Okay, wait. Okay, so this one. Okay, if you haven't done it, if you haven't tried yet, try to understand and think about these questions. Okay, so it's about adiabatic steam turbine. So I've mentioned here, written here to look at the table A6, but actually at least you understand first the okay, once you get the problem or questions about the case concerning thermodynamics, okay, especially about the first law, energy balance, etc. Try to locate first the situation, the location of inlet and outlet. Okay, point 1, point 2 of the example of the problem in a TS diagram. Okay, try to imagine first, try to sketch in your notebook, or try to sketch or try to imagine first the TS diagram. Okay, temperature versus entropy. Okay, we haven't learned entropy yet. If entropy is actually concerns second law of thermodynamics. Okay, but at least you can draw, just sketch first the process, even though we are not going to calculate the entropy. Okay, but at least we know the position, how to locate the inlet outlet. Okay, the process in a TS diagram. Okay, so you need to understand it first, so that from there we can know whether the location, the inlet or the exit is at a superheated or at a compressed liquid or saturated vapor, saturated liquid, etc. Okay, so always try to first, when you get the problem, thermodynamics, try to locate first, try to imagine at which location in the diagram, in the graphic, which location is the inlet and outlet. Okay, that is going to help you to choose which table to understand the process. Okay. Okay, so for those who have entered, I understand that you guys just finished another class. So today I'm not going to start a new chapter yet. Okay, so I'm just going to do extra, more example, more exercise concerning the first law, energy balance. Okay, to enhance more your understanding on this topic, first law, before we proceed with the second law. Okay. So I'm using the same slides, chapter 6, just that I've modified a bit the questions and I've added another 2 more questions. Okay, so we start with this one. It's about steam turbine. Okay, so when we mention first let's look at the keyword or the important words in the questions. Okay, what do we know? It's a steam turbine. Okay, turbine. When you talk about turbine, what is the process? The process that occur in a turbine. Okay, I'm going to ask someone at least to see whether you understand or not the process. Okay, Amirul Akmal. Amirul Akmal, in a turbine, usually what process occurs in a turbine? Apa biasanya proses apa dalam turbine ni? Apa yang berlaku? Proses apa? Okay, example. Apa?
I forgot.
Okay, just a bit of hint, something like this, whether it's evaporation, boiling, condensation, compression, expansion, or any other thing.
In the turbine, right?
Yes, turbine.
Is it compression?
No. No, not compression. Compression, which device? Compress, to compress. To compress you use what? Kalau compress nak guna apa nak compress?
Ada pressure.
Yeah, so what is the device to you that you use to compress gas, fluid? Apa device tu?
Alamak.
Compressor.
Compressor, okay. Compressor, okay. Compressor or pump, okay, dia blur, tak apa.
Okay.
Kita warm up sikit dulu, okay. Compressor, okay, it's true. Compressor for fluid, gas, vapor, steam, compressor. But for liquid, we use pump usually, but the function is the same, to increase the pressure, to compress. Okay, so pump is for liquid, compressor for gas, vapor. Okay, steam. Okay, so turbine, what is the process happening occurs in the turbine? Apa? Wants to answer? Okay, Amirul Akmal nak try sekali lagi ke? Okay.
Orang lain dah terlalu ni.
Okay. Tadi Khairul dah tolong. Eugene Raphael. Eugene, sorry. Okay. Which process occurs usually in a turbine? You want to understand first the process in the question number 3. Proses apa yang biasanya berlaku dalam turbine ni? Jadi just now I give yes, you want to answer?
Tak ingat.
Okay, I give some example just now. Okay, it's already narrowed down. Okay, so whether it's a compression, okay, to compress, to increase the pressure, expansion, condensation, or evaporation, boiling, or what? Which process of thermodynamics? Turbine kita guna untuk apa? What do we use turbine?
Compress.
Seorang lagi compress. Jadi salah lah. Just now Amirul Akmal mention it, but it's wrong. Okay, okay, it's okay, Jane. Ramai tengah tidur lagi ni. Tension, you want to answer? Combustion not only. Sorry me. The combustion is okay. Combustion is one of the process that can occur in thermodynamics. But turbine.
Is that evaporation?
No.
Condensation?
No. Okay. Okay, thank you, no.
Because
okay.
It's using the heat to like spit out the turbine to generate electricity, right?
Yes. Usually in the end, in a turbine, we produce power. So that's why here it mentioned the power output of the steam turbine. The power produced by the steam turbine is 5 megawatt, etc. But what is the function, the process of the turbine? At least if you mention function.
Doctor.
Yeah.
Is it combustion?
Tak. Umi dah jawab dekat tepi ni, salah.
Oh, tak perasan.
Combustion chamber lah. Combustion, if you want the process of the combustion occurs in a combustion chamber. So you burn or burner, you burn the fuel with the air, oxygen. So you we get the combustion process, but not in the turbine. Maybe I think you guys confused with the gas turbine. When we mention a gas turbine, okay. So I have mentioned just now the like option A, B, C, D. So you guys have chosen all the A, B, C. The only one that you haven't mentioned is the D, which is the answer. It is the expansion. Okay. So it is the opposite of compressor. Okay. So compressor to compress, increase pressure. Turbine is expansion to decrease the pressure. When we decrease the pressure and temperature also, then we will produce power output. Where we generate power from there. Okay. Okay. So I think maybe you confused with the gas turbine. Okay. So usually we name gas turbine. How to say? Okay. A gas turbine cycle is like a name, okay, of a thermodynamic cycle. We call it as a gas turbine cycle. Okay, but when we mention gas turbine cycle, it means the whole process, the whole process of the cycle, which includes compressor, right? Compression, evaporation or combustion chamber, combustion process, and then expansion, and lastly condensation. So there is four basic. Okay, I think I have to kita contoh sikit. But this concerning this gas turbine cycle process, you will learn later on, gas power cycle, etc., Brighton cycle for aircraft. Okay, you will learn in the next few chapters. But I just mention here first. So because I think most of you confused when in the questions just now it mentions steam turbine, but usually the one that we heard is a gas turbine, right? Okay. So gas turbine cycle, okay, I draw a diagram of a basic cycle. So like this macam mana lah. Inilah kot. Okay. This is closed cycles, closed thermodynamic macam mana lukis? Turbine cycle. Macam ni. Okay, so this is pump or compressor. Okay, so this is pump or compressor. This is for a closed cycle. This is not aircraft engine cycle yet. Okay, a closed power plant cycle. So we have here evaporator, not combustion chamber. Kalau combustion chamber usually for open cycle or aircraft engine, combustion chamber. Untuk power plant, by using gas or liquid, here we have evaporator or boiler. So boiler usually is for liquid, evaporator for gas or vapor, okay? Vapor. Same here, compressor usually is for vapor, gas. Pump is for liquid. The function is the same, the function same, but the device used is different, okay? Compressor is for vapor, gas, pump is for liquid, water, etc. Okay, so this is, here is turbine. Okay, so turbine where we have expansion process. So since it is a cycle, so the process is like opposite of each other. So usually we will start first at pump, compress. We compress the vapor, the gas or the fluid. Okay, compress, increase the pressure and increase also the temperature a bit. And then the fluid will be evaporated, will be boiled or evaporated and exchange heat with the heat source. If we have a heat source, fuel as heat source, or sometimes we have solar energy as heat source. Okay, that is the heat source that has to be given to the evaporator, so that the fluid inside the cycle, the cycle can exchange heat, so that it can evaporate. When it exchange heat, it will evaporate, okay, with the heat source. And then turbine is the expansion process. Okay, so ideal case here, usually here constant pressure, ideal case, not the real case. Usually we have a pressure drop in the evaporator or combustion chamber. Okay, so here turbine, decrease pressure, expansion, pressure will decrease, and condenser is the opposite of the evaporator. So from vapor to liquid, vapor to liquid to condense back, so that we can continue back the cycle. Okay, so this is a cycle. This is a basic gas turbine has. So this is the whole of this is what we call gas turbine cycle. Okay, gas turbine. Okay, even though the name is turbine, okay, turbine, but it's actually when you mention gas turbine, it's the whole cycle, the whole thermodynamic cycle, which is consists of these 4 component device. Okay, the 4 process. This is the basic 4 process without reheat, preheater or regenerator, etc. Not yet, just the basic cycle. So if we have at least these 4 component, these 4 process, we can produce power. So from the turbine here, we will produce power generator, power, mechanical power, electrical power. Okay, so the whole of this is what we call gas turbine cycle. Okay, so we I'm not sure why they choose the name of gas turbine cycle, but obviously because the turbine is the one that in the cycle, turbine is the one that is going to produce the output that we want, the outcome that we want from the cycle, which is power lah. Okay, the work done of the cycle is produced in the turbine, but the complete process is 4. So I think, I'm not sure, but I think that's why they call it as gas turbine, the whole this cycle. Okay, so back to our question just now. Okay, our questions here, the power output of an adiabatic steam turbine. So in this question, it just concern the one component turbine just now. Okay, the only one, not the whole cycle. Okay, we just going to look at the turbine, only one component. Okay, so what process occurs in the turbine is expansion, decrease pressure. We decrease pressure, we decrease temperature also normally. Okay, so that is the function. So we have to understand first, even though the question is short, only 1 sentence, but you have to understand first the process, can? So from there you know how to locate which table to use, how to calculate, etc. Okay, so we now, it is an expansion process. Okay, steam is like vapor, vapor, gas, etc. Okay, it's just how to say, generally steam and vapor is the same thing. It's just that in thermodynamics we are being extra careful with the use of the certain words, because in thermodynamics usually steam is something that is a vapor that is near saturated line. Means it's just being the gas is just being done evaporated. Okay, so that's what we call steam. It still has a minor liquid in there. But usually when we use in thermodynamics, when we use the word vapor, we understand that it is a superheated gas. Means you already there's no more liquid portion of liquid in there. So when we mention vapor, we understand that it is a superheated vapor. It's already being really evaporate lah. Okay, dah habis dah, betul-betul dah macam tinggal vapor lah. But normally when we use we mix together, we blend together these words, steam, vapor, kita anggap macam sama. We suppose it's the same, but just in thermodynamics the definition actually is different. Okay. So and then adiabatic also, it concerns a second law, but I'm just going to explain a bit. Adiabatic means that the system, here the turbine, do not exchange, we assume that the turbine do not exchange heat with the ambient outside. Okay, so it's like adiabatic lah. Okay, so the power output, so inlet, so we are just going to focus on the turbine, the expansion process of the whole gas turbine cycle. Okay, so now now that we know we have expansion process, another maybe useful tip, just now ni apa steam okay, steam, so it's like water. TS diagram that I mentioned. Okay, I usually use TS diagram. Okay, we can also use PV diagram, HS, etc. But TS is the most convenient lah for a gas to sketch, to locate, to represent gas turbine cycle. Okay, even though this parameter S, entropy, we haven't learned yet, but it's okay, we're just going to sketch it. Okay, we are not going to calculate it yet. Okay, so TS diagram, if you Google, or if you have the thermodynamic books or any thermodynamic books, okay, you can also Google the TS diagram. Okay, it's kind of like this. Dia macam bukit sikit, saya just nak make sure. But there are certain fluid, dia apa, the mountain is a bit sengit, okay, tilted. Okay, but for water, I think it's kind of like this lah. Let me check. So because here it mentions steam, so so steam is like water lah. Mana TS diagram tu? The TS diagram for water. So it's kind of like a mountain here. Okay, and then so just to understand the process of gas turbine cycle, the cycle. So I will sketch an ideal cycle. Okay, ideal cycle. So this is a compression process. We start with compressor first, compress. And then curve, okay, like this. So here compression from point 1 to 2. Okay, normal gas turbine 1 to 2. This is compressor. I know it. C, and then we have this one 2 to 3 is the evaporation process in the evaporator. Okay, from 2 to 3. Okay, and then 3 to 4 ideal case. Ideal case is what we call isentropic. So it's actually a straight vertical line here. Ideal case. Kalau bukan ideal, if not ideal, there is some pressure loss, some loss in there. Okay, so here is number 4. Okay, and then back. So this is expansion, turbine, okay, and this is condenser, condensation. So condenser from liquid vapor to liquid. Okay, so this is the liquid region, this is the vapor region. Okay, along this line until this one, this is saturated liquid, and along the from the peak until this line, okay, this is the saturated vapor line. Okay. Okay, so now we are only focusing on this expansion process, turbine process. Okay, we're only focusing at this point. Okay, 3 to 4. We forget about this first. Okay, just focus on the 3 to 4 turbine. So you mentioned here the power output of an adiabatic steam turbine. Okay, so at location 1, we have P1 pressure 2 megapascal, T1, V1, Z1. The Z is the altitude, the location, because we want to calculate potential energy. Okay, so here it use number. Okay, so we forget about this first. Okay, so we focus on just turbine. So one here, two here, okay? Inlet outlet of the turbine. Okay, so point one should be around here. Okay, this is just what we imagine. Okay, maybe after you calculated the value, you evaluated, analyzed, etc. Maybe the point one is not exactly on the saturated vapor line. Maybe it's a bit off, or a bit inside. So this is just from what we understand the process. So we start to sketch first, so we understand, we know how to locate the inlet outlet, etc. Okay, so point one given, P1 T1, so we expect around here the P1 is 2 megapascal, so here is 2 megapascal. Okay, just look at the question lah. T1 400 degrees Celsius, V1 50 meter per second, and Z1 10. And then the two outlet is 50 megapascal. So here P2 15 15 mega to 15 kilo. 15 kilo, sorry. 15 kilo. So look at here. The pressure is decreased. Alright. Pressure decrease from 2 megapascal to 15 kilopascal. So the pressure is being decreased. So it is an expansion process. Okay. And T2 is not mentioned. T1 X2 90%. Okay, the quality at the quality of the vapor. Okay, the fluid at point 2 is 90%. Means this one 90%. We went, okay, first X2 90% or 0.9 quality. Quality means that the steam, okay, kalau 90% means that 90% of the steam is in vapor phase. Only 10% is in liquid phase. Okay. So when mentioned here quality is 0.9, so we understand it's actually the point 2 has to be really near to the saturated line. Maybe it's actually like here. Okay, really close to the saturated vapor line, nearly becoming fully vapor, nearly. So actually sepatutnya point 2 ni kena dekat lagi lah kat sini. Sebab tadi kita just sketch je kan, just nak tahu kan. Okay, so you can try to locate the each point so that you understand the process. Okay, so what else? Z okay, V okay, okay. So you can look at the information data given here also. V1, V2. Okay, V1 50 meter per second. Sorry, okay, V1 50 meter per second and V2 180 meter per second. So the velocity of the steam is being increased also from the inlet to outlet of the turbine. So here it shows that turbine can increase the kinetic energy, the velocity, the speed, okay, while expanding, while decreasing the pressure. Okay, so we have finished analyze the questions. Okay, even though it's just one line question, but there's a lot of things to analyze, to understand first. So now we know the location of point 1 and point 2. We assimilate the location, approximate the location. So now how to start? Okay, so first compare the magnitude and data H, data KE, kinetic energy and potential energy. Okay, I think kinetic energy and potential energy is quite direct because we have altitude, we have velocity. So we start with enthalpy first. Okay, the enthalpy is the one that we have to calculate and look up in the table, etc. Okay, so enthalpy. So how to calculate enthalpy? Okay, so maybe we can start with by writing the energy balance of a steam turbine. Okay, try to write down first the energy balance of the first law of thermodynamics for this, apply to this turbine. Okay, saya bagi masa sikit. Okay, with all the information given, how is the energy balance going to be? Okay. You can look up in the slides also, chapter 6. I think there is it's already written there, the energy balance for a turbine. What does we assume? Okay, here I've written table A6. So table A6 concerning superheated vapor. Okay, so why we choose superheated vapor? Okay, the inlet point 1 is here. Okay, is either at the saturated point or is above the saturated point, which is here. This region is what we call vapor, superheated vapor. Okay, so we are going to use table A6, table A6, superheated vapor 4.1 to get the enthalpy H1. I'm not sure if I've given, but you can also search. WhatsApp group. Table A6. If you haven't have it yet, okay. The table A6, superheated vapor, superheated water lah, steam kan. Here. The substance is water, okay, just that the phase, okay, the phase of the substance is in vapor, superheated vapor. So 0.1, 2 megapascal. So just look at the 2 megapascal pressure, and then temperature 400 degrees Celsius. So what do we get for H1? Okay, saya tukar-tukar slide. Okay, so this one, okay, 2 megapascal, 400 degrees Celsius, saturated temperature. Okay, so it's along the saturated 0.1 saturated vapor line. So 400 degrees Celsius. Sorry, and this one. So H enthalpy 3248.4. 32.84.4, 3248.4. 2 megapascal, 400 degrees Celsius, superheated water. Okay. So 3248.4 H for H1 enthalpy 1. Okay, settle. Okay, settle. Understand, everyone? Semua okay? Untuk point 1 first. H1. Yes. Okay, okay, then H2. H2. Okay. Look back at the diagram. Okay. Where is H2? Where is point 2? Point 2 with quality given 0.9 or 90%. So we understand that point 2 is a mixture of vapor and liquid. Okay, it's not totally vapor, not totally liquid, but it's a mixture. So means that it is in the inside the mountain there. Okay, before it goes to the condensation process. So when it is a mixture. So we use we have to use the quality given here. So H2, we use this one, H2, HF plus X2, HF G, sorry, writing. Okay. So H2, we have to calculate H2 equals to HF plus X2 HFG. Okay. So this one, table yang dah ada ni, table apa tah? A4 ke tak ingat lah. Seperti A6, A4. Temperature given 2372. Berapa tadi? 15 kilopascal. Okay. Okay. So I don't remember. This is table A5 or table A4. Okay. The one that I've given earlier, previously. So 15 kilopascal. Okay. Pressure 15 kilopascal. Okay. So we take HF at 15 kilopascal. Saturated liquid vapor is 225.94. And the enthalpy of the evaporation process is 2372.3 HFG 2372.3. Okay, understand? Look at the line 15 kilopascal saturated water, which is a mixture of liquid and vapor. Kita nak cakap okay so how to locate this one? So actually HF is this one tau. This one. What you looking for from the table, HF is this one. HFG is HFG is the macam the difference. Okay. H2 is this one, H2. Okay, so we are going to search for H2. Okay, fluid F kita tahu. Okay, so using this one, HF just now 225.94. Saya masih tulis ya. 22.94 susah sikit. 225.94 plus 0.9 HFG 2372. Okay, from the table just now, 0.3. So we get H2. Okay, should be around 2000 something lah. Okay. Okay, H2, calculate H2. So H2 around 2361 kilojoule per kilogram. Don't forget the unit. Kilojoule per kilogram. 2361. Okay, so now we have H2 and we have H1 previously from the table. Okay, so back to the questions. Back to our questions. We want to search for delta H. So delta H just H2 minus H1. H2 minus H1. And then for kinetic energy is V2 square over 2. So V2 square over 2 V2 square minus V1 square over 2, the difference of inlet outlet kinetic energy, and then Z potential energy is GZ lah. Okay, so delta H, okay, H2 minus H1. So you obviously you will get something negative. So means that the enthalpy, okay, decreasing, okay, and then delta KE, kinetic energy, V2 square minus V1 square over 2 kinetic energy. Kinetic energy must be positive because we see that the velocity increasing. Okay. And PE, potential energy, the gravitational force, Z2 minus Z1. Okay, Z2 just the altitude. Okay, 10 minus 6 I think. 10 minus 6, just 10 minus 6. Okay, so we see from here, 6 minus 10, sorry. So the potential energy also is decreasing. So we see from here, one thing that is that the potential energy is very, very small compared to the enthalpy and kinetic energy. Even kinetic energy also is quite small. The main consumption of energy is the enthalpy, from enthalpy. Okay, means the internal energy, pressure, temperature, the energy caused by the pressure, temperature, etc. Okay, so the kinetic and even potential energy is very, very small. Okay, so around negative 0.04 for potential energy and kinetic energy around 15. Okay, kilojoule per kilogram. But the enthalpy is around 800, 900 kilojoule per kilogram. So that's why in ideal case, sometimes we neglige the potential energy and the kinetic energy compared to the enthalpy. Okay, but if you want to calculate to sum up, total up all of the energy also can, so that the answer will be more accurate. Okay, so that is number one. So you just calculate the answer, calculation, just do the calculation. B, determine the work done per unit mass of the steam flowing through the turbine. So usually for thermodynamics or even propulsion later on, it's always the first questions that maybe took you a longer time, because we need to understand the process first and how to locate where is the inlet outlet, and then BC is just the application. Okay, so B is actually work done per unit mass. Okay, so you just total up. Okay, so work done is from the energy balance. Okay, the energy balance, we have work, we have heat transfers, but here in the turbine, since it is adiabatic, so no heat transfer from the outside or from the outside or from the inside to the outside. In out tak ada. Okay, so it is adiabatic, so no Q, no heat transfer, okay, in the energy balance of the turbine. So only enthalpy, kinetic energy, potential energy, and work. Okay, so from the energy balance, since we already have enthalpy, kinetic, potential, so we can conclude, we can derive the work. Just use the energy balance equation. Okay, just masukkan balik in the equation. Okay, so remember the definition. I just write down back the definition. Maybe you forget about this. Since we have semester break and all, so this is the energy balance. Okay, so it is a steady, steady, so equals to 0. The rate of change of the energy in the outlet. So at point 1 mass. Okay, so the mass is constant. So we have GZ1 at the inlet equals to outlet. Oops, ada yang belum masuk. Equals to outlet W out. Power produce. There is a power produce out. And apa tadi? Okay, and plus the same thing here. M dot H2 plus V2 square plus GZ2. Okay, Since Q is adiabatic, so Q0. Okay. So here, so we have all these value H1, H2, V2, etc., etc. The anything from question A, and mass can be cut out because here this is like this. Okay, in terms of mass, so small. Okay, so so can cut the mass here also. So we want the work work done. Work done per unit mass, so we can leave it the answer in per kilogram. Okay, so just calculate, just use this one. So we have around 872 kilojoule per kilogram. And finally, it's getting easier. Calculate the mass flow rate of the steam. So the mass flow rate of the steam mass. So we have the value of the power output 5 megawatt. So we just use it. So 5 megawatt is 5,000 kilojoule per kilogram. Divide by 872. So we have our mass. Okay. Okay. Any questions for this one? Turbine, so remember turbine, it is an expansion process. So decrease pressure and we produce power output. Okay everyone, ada soalan tak? Zainul okay? Umi okay?
Yeah, okay doktor. Good.
Okay ke Umi?
Yeah, okay.
Ada soalan tak? Tak ada. Digest. Okay. Second question. So number 4 in the slide. So number 4, is actually quite, the same method as previously, just now, steam turbine. So air at 100 kilopascal and 200 Kelvin, 280 Kelvin is compressed steadily to 600 kilopascal and 400 Kelvin. The mass flow rate of the air is 0.02 kilogram per second and the heat loss of 16 kilojoule per kilogram occurs during the process. Assuming the change in kinetic and potential energy are negligible, so it's easier, we neglect directly KE and PE. Determine the necessary power input to the compressor. So this time we want the power. Okay, just now the power is given. Here we want to calculate the power input. So turbine and compressor is the opposite process. So turbine, expansion, decrease pressure, we produce power. Compressor, we use the power that is being produced by the turbine. We reuse the power, okay, the power input, give the power to the compressor so that compressor can compress the fluid, okay, the air inside, and it increase the pressure, increase temperature. So it is the opposite, okay. So it's actually the power used by the compressor is where, for example, if you in our house we use what we aircon, refrigerator. Okay, so the electricity power used to calculate the electricity power used by our house, refrigerator, aircon, etc. So here it is from the power of the compressor, power input in the compressor. So power yang kita guna untuk compressor itulah power yang kita calculate untuk berapa banyak electricity kita guna untuk satu-satu device itulah. Okay. So sebab tu that's why if our house compressor rosak, the compressor is broken down, aircon electricity jadi mahal lah. Salah satu punca lah. Okay. Salah satu one of the reason usually electricity in our house goes up, or there's any problem in the aircon, we have to check our compressor. Okay. Maybe the compressor needs to service, maintenance. Okay. So here, This one I let you think about it, because it's quite the same method as just now. It's just that opposite. This time we have compressor, so compressor, compress, increase pressure. Okay, try to do this one. Number 4 first. Nanti saya panggil nama lah ya. Sebab I already show how to do it in previous one. So this one you try. In the meantime, okay, actually this week I have to give you kind of like assignment, but not assignment as in project assignment yet. Just like a homework, case study problem case study to solve. But I will upload it maybe at the end of this today. Okay. So you have to submit the homework or the assignment in 2 weeks. Okay, so you will have, as I've mentioned in the intro at the beginning of the semester, first week, I will give you around two assignment, kind of like a homework, okay, case study. Actually, it's like a just problem like this one, but a longer version. Okay, so you have to solve the problem. And then a more like group assignment, not really group, like pair assignment, I will give maybe around 2 to 3 weeks more to come. Okay, since we don't have test 2, so we need to do we need to have at least something like a homework or case study, something like that. Okay.
Doctor,
Yes.
I want to ask about like the percentage of each like assignment test. Like test 1 is 15%. What about the rest of the 60%?
But test 1 is usually 20%. Okay. 20.
Oh, 20%. Okay, sorry, my bad.
Okay. Actually, I've mentioned at the beginning of the semester. So I'll share back the slides. Introduction. This one. Okay. Okay, so assignment around 20%. So I think I will give 2. Okay, so 10%, 10%. Project, this one in pair or 2 or 3% in group. Okay, so since you guys are not too many, only 13 of you. And then test 1 already done, 20%, and final exam 40%. Okay.
Yes, thank you, Doctor.
So back to the questions. Sorry, I'm talking but I'm muted. Okay, again, sorry, I will show you how to locate first the point in a TS diagram. Okay, it is slightly different than just now previously because this one, the fluid is air, totally air. Okay, so that's why we use compressor, we don't use pump. Okay, pump is for liquid. So here is air. So the location in the TS diagram is slightly different. Okay, so just now, okay. So in a TS diagram, the process, the gas turbines, if you have a gas turbine cycle for this one, it's actually like this. The 4 process. in the, sorry saya punya curve ni tak lawa. Sekali lagi. The for process in a TS diagram. Okay, so we just focus here. We just focus this one. Okay, the compressor. Just focus. This one is the evaporator. This one is the expansion, and this one below is the condensation. Okay, so we just focus on the compressor part. So it's like this. Compressor. Okay, 1, 2, 2. Compressor air. So different from the just now previously. The TS diagram just now. So it's actually this one. So this cycle is actually located around here. Imagine is located around here because it is not liquid. We don't have liquid. And it is not a mixture of a liquid and vapor as well. So it is positioned around here. Okay, so that's why we don't have the mountain. Okay, so it's actually around, for example, around here. The process is around here. Okay, around here. Okay. So that's why for this one we don't have no. Imagine the mountain is actually over here. Okay. So we have totally vapor. Compressor. Apa lagi ni? Okay. So this one compressor air. So okay. So I already sketched it. So how going to we want to calculate apa tadi? Power input and power. So of course power we need to use the energy balance. The first law of thermodynamics, the energy balance apply to a compressor. So I'm going to call Eugene. Eugene, Rafael. I am afraid I pronounced your name wrong. But it's Eugene. Can you can you open the whiteboard here, the link? The link is in the chat. Can you open the link? Okay. Can you enter the whiteboard?
Yes.
Okay. Try to but using the whiteboard. Okay, write first the energy balance equation apply to this compressor. How is your energy balance equation going to be? Write down on this page, page 4, below or above. Write down your energy balance equation of the compressor.
Betul.
Okay, sorry. Okay. Okay. This is your energy balance for compressor. Okay. It's just that you have to add point on because it is in a mass, flow rate. So kena ada point.
Oh.
Quite different, okay. Okay, okay, thank you. Everyone, this is the energy balance applied to the compressor. So since we don't have the potential energy and the kinetic energy is are negligible, and then we have heat loss, given heat loss 16 kilojoule. Okay, and work input lah, the power given to the compressor by the turbine. Okay, so we have this. So now what we have to do, Q out is given, so settle. Mass also given 0.02 kilogram per second. So we only have to search for H2 and H1. Okay, enthalpy. So we're going to use one of the thermodynamic tables. But which table? Okay, H2, H1. H2, H1, nak guna table mana? Zainul, Arifin? Which table are we going to use for H1 and H2, to get H1 and H2 enthalpy? Nak guna table mana? We can see the link there, but sorry, tak nampak. Zainul, are you there?
Yes, okay.
Okay. Which table are we going to use to search for, to get H1 and H2 enthalpy? H1 first. Table mana? Saya dah lukis CS diagram. Tadi saya dah kata location dekat mana. So I hope that will help you to choose which table and which state the fluid are in. Table mana, Zainal?
Table acid ke tu?
Kuat sikit tak dengar. Apa dia?
Table acid ke?
Acid siapa superheated water ke?
Yes.
So how you going to read from there? Superheated water tu macam mana nak baca? We nak akan try, for example H1. How do you get H1? Okay, saya buka. Kalau this one superheated water. This one kot This one, we're talking about this one. Ni ke? A6 kan? A6 this one kan? Cakap tadi. Ni bukan ni A4. Yang mana? Zainul.
Saya belum pasti.
Okay, dah kalau you kata A6 tak apalah. Apa ni, yang mana dekat mana you nak tengok ni? Value H1 tu. H1 0.1, air at 100 kilopascal, temperature 280 Kelvin. We have the pressure and we also have the temperature given. So we are going to search for enthalpy. H1. Nak guna mana?
Is it 2828.3?
Yang mana? Yang mana? Which one? Dalam table yang mana satu? Pressure?
Table untuk pressure 1.0 megapascal dengan saturation temperature 200.
0.1 megapascal tu 0.1 megapascal 100 kilopascal and 280 Kelvin tu We don't have to add 80 Kelvin here. So you are proposing to use what? 300 Kelvin? Are you proposing that? Itu ke yang awak cadangkan? Pressure P 0.1 megapascal, temperature, saturated temperature 300. Itu ke yang awak cakap tadi? Here we have temperature 280 Kelvin. Kelvin, so 7 degree Celsius je sebenarnya.
Okay. Saya keliru ni.
Okay, but it's okay. So from here, you and the others understand kenapa kita tak pilih kan table ni, kenapa kita tak pilih table ni, why we don't choose this table, why we choose another table, right? Okay, so I'm going to explain. So we cannot use this one. Okay, even though it is superheated, okay, superheated water here. So I think maybe that's why Zaidul thought about this table, superheated, but we cannot use this one. One thing, apa tu? The temperature given here is saturated temperature. Temperature is in degrees Celsius. Okay, so starting from 50 to 1000, etc. So we only have here the air is only 280 Kelvin. Very small, quite small. So normally we start the compression at a really small pressure and temperature. Okay, so we cannot apply this one. Okay, we cannot apply this table. We cannot use this one. Okay, so what other proposition table that we have that we can assimilate? Plus another thing. Another thing. Why we cannot use this one? Okay, you need to understand also why. Other than due to the temperature. That's why the TS diagram just now is very important. Okay, I look back at the TS diagram. Okay, here this one, the one that I draw just now. Okay, so we are searching for the H1 location 1 here kan. Okay, so it is a compressed air. Okay, remember the questions, compressed air. Air. So air, vapor, gas lah, not liquid. Okay. So compressor, again compressor. If you look back at the TS diagram previously, this one, if you said that if you want to use the table A6, if you want to use, why we cannot use table A6? Because if you use table A6, the compression process here is occur in a liquid phase. Okay, compression process kalau biasa ni the liquid phase, which is starting from the around saturated liquid line. But here we have air, so we cannot use that one. Okay, it's not the same process. Okay, so sebab compressor dia either dekat sini atau dia totally itulah kan. Dia bukan dekat sini. Just now the table AC is superheated water kan. So if you took the table A6, the process in the compressor should be liquid, but table A6 mention superheated water, which is it should be vapor. So tak boleh lah. Okay, faham ke? Understand tak? Do you guys understand? Okay, table A6 is superheated water. Superheated means that vapor. Table A6 just now, table A6 concern superheated, which is a vapor. But we understand if compressor, kalau compressor process biasa, liquid, vapor just now, from liquid change to vapor and back to liquid, the compression process is in a liquid phase, bukan not superheated vapor phase. So we cannot use A6. This time, this one is air, means vapor. Okay. Just now I think someone want to ask questions. Diorang nak tanya soalan ni. Just now I think someone want to ask. No?
No, we were just saying yes, doctor. Like we understand.
Said, Hamdan, you understand, right? Okay. So not table A6. So what else? Or which table? Kau tak ada lagi. I think I've already given this table. Okay. It is ideal gas table. Okay. So ideal gas table. Silap tekan. Ideal gas table. Banyak sangat ni. Sorry. This one. A17. Saya bagi sini. Okay, this one. Tapi but this one A17 Ideal gas. Wait, I have questions here. A17, yes, Omar. A17, so we use ideal gas. Okay? So we assume that the compressed air is an ideal gas. That one we can assume. Okay? We can assume because it is a gas. It is air, gas, vapor. So we can assume that it is ideal. Okay. So this one, because we use this one, 280 Kelvin, 280. Okay, we have 280. The 10th line number 10. No, number 10, number 1, 2, 3, 4, number 9. Okay, 280 and so just take H 280.13 to 80.13. Look at this table. Temperature 280 Kelvin. H is 280.13. Okay, so that is our H1. Oh, betul. Okay. I thought I didn't change the tab. Okay, so 280.13 H1. And then H2 exit the compressor 600 kilopascal and 400 Kelvin. 400 Kelvin. So using the same table because it the inlet and outlet of the compressor is air, same phase. So we use the same table, 400 Kelvin. 400 Kelvin, the H is 400.98. 400.98, this one. 400.98. Senang ya. 200, 280, 400, 400.98. Okay. Okay, so that is your H1, H2. So just substitute in the equation that Eugene have written just now. Okay, so just substitute here. So you have H2 for 400, sorry. H1 280, mass 0.02, Q up 16, and you get the power input. Alright, that's all. That's all for question this one. Okay, so it's easy once you understand the concept, once you understand the process. So that's why it's very important to locate first the process, in a diagram, sketch it. Okay. So any question for this example about compressor, the process in a compressor? Any question? Mutaman, just now I saw him, then he left. Kara Rushdie okay? Niza okay? Faham tak yang compressor? Compressor ni lain sikit because the phase phase lah, fasa. Substance to water tu sekarang dia air, dia totally air. Dia tak ada mixture macam tadi. Sebab kalau dia macam yang tadi, proses compression tu should be in a liquid. Proses compression tu dalam liquid, dia bukan dalam vapor, air apa semua. So bila dia dalam totally air, so kita tak boleh guna table yang tadi tu. Tak sama. Okay, last one for today. Number 5. Okay, this one is refrigerant. Okay, refrigerant R134A it is an organic fluid. So it's not water. So obviously you cannot use table A6 ke, table A13 ke apa. Yeah, water not the same. Okay, so you have to use other table. Okay, so refrigerant 134A is to be cooled by water. Oh, sorry. Okay, refrigerant 134A is to be cooled by water in a condenser. Okay, so now we have a condensation process. Okay, just now we have seen turbine, expansion, compressor, compression, now condenser, condensation. The refrigerant enters the condenser with a mass flow rate of 6 kg per minute at 1 megapascal and 70 degrees Celsius and leaves at 35 degrees Celsius. So ensure the unit of temperature sometimes it is given in Kelvin, sometimes it is given in degrees Celsius. The cooling water enters at 300 kilopascal at 15 degrees Celsius and leaves at 35 degrees Celsius. Neglecting any pressure drops, so we assume either process, no pressure drop, no pressure loss. Determine the mass flow rate of the cooling water required, the heat transfer rate from the refrigerant to water. Okay, what you have to understand first, condenser, evaporator, boiler, what else? Preheater, regenerator, etc. Reheater, reheat. Okay, those are heat as what we call heat exchanger. So when we mention heat exchanger, a device named heat exchanger, you can Google it. Okay, heat exchanger. So heat exchanger can be several types. Okay, there are several types of heat exchanger. Okay, the function is the same, are the same. They are used to exchange heat exchanger to exchange heat. Okay, but there are several types of heat exchanger, and condenser, evaporator, boiler, etc. are example types of heat exchanger. So you have to understand that. Okay. So when you understand that, so the means that the process occurs in those condenser, evaporator, etc. It is like a heat transfer, heat exchanger process. Okay. So that's why in the chapter 6 slides, we don't have specific theory about condenser or specific specific equation about condenser, specific about evaporator, etc. Because those are heat types of heat exchanger. It's just that the process occurs is different. Okay, evaporator from liquid to vapor, condensation. Condenser is from vapor to liquid. Okay, so here we want to focus on the condensation process. But how we going to evaluate, to analyze the process, we use the same method of analyzing a heat transfer, heat exchanger process. Okay, means that exchange heat. So what happened here? Umi jatuh what happened here? Okay, so when we mention heat exchanger, means that there has to be at least two fluid. Okay, two fluid, gas, vapor, or liquid and vapor, or gas, vapor, or liquid. Okay, there must be at least two fluid because they have to change with each other. Okay, kalau dia tak change lah, tak exchange lah. The heat has to be exchanged with each other, so at least we have to have two fluid. So what are those two fluids in these questions? First one, those two fluids are refrigerant 134 and another one is water. Okay, so we have these two fluid inside the condenser. Okay, the heat exchanger condenser, refrigerant and water. Okay, so from the data given here, the information given, we understand that refrigerant is to be cooled by water. Okay, so to be cooled, so refrigerant is the hot fluid. Okay, because it is going to be cooled by water, means it is from hotter side to cooler side, cooler temperature. And water is going to get colder from it used to be cool by water from cool it's going to get warmer from colder temperature to a warmer temperature. Okay, so means that we use water to cool down the refrigerant inside the cycle, inside the condenser. Okay, so it's normal. If you have a power plant, gas turbine cycle used for power plant to generate electricity, mechanical power dekat kilang-kilang kan. So we need we call it coolant. So the coolant can be, usually it's water. We use water to as the coolant, cooling water to cool down the working fluid, which is refrigerant here. Or sometimes it is the environment, ambient. The environment, the ambient is the cooling side. Okay, so here we use water to cool down the refrigerant. The cooling water enters. Okay, so here we already have all the information, pressure, temperature, right? So from 70 to 35 degree, and from 15 to 25 degree. So I'm going to just draw here. What time is it? 12:30. Yeah. Can I draw? Okay. Something like this. Okay, kita buat. Saya ingat. So and then normally buatlah macam mana okay. This is the heat exchanger. So one fluid is going to go inside the tube pipe here, and another fluid is going to masuk dalam compartmentnya. This go into this compartment in the outlet. Okay. So there are two types of fluid here. Cooling water. Okay, so this one normally the one is going to flow inside the tube is the water. Refrigerant. So this is the refrigerant. 134. Okay. Okay, so it's going to they are going to exchange heat inside this heat exchanger, and the process is what we call condensation. Okay, so inlet outlet. So this is inlet, this is outlet of refrigerant. R134. This is water inlet, this is water outlet. Okay, this is what happened in the condensation process. Okay, now apa tadi? So we have the refrigerant enters the condenser 1 megapascal. So here P 1 megapascal, T 70 degree. What else? Okay, and leaves at 35 degrees Celsius. So here T 35 degrees Celsius. No pressure loss. Ideal case, negating any pressure drop. So pressure should be the same, 1 megapascal juga outside ni. Okay, and then water. The cooling water enters at 300 kilopascal, 15 degrees Celsius. So 300 kilopascal here. So when you get soalan, a question, tutorial, exam, etc., try to sketch down and write down all the information given. Okay, so you can understand clearly the problem. T 15 degrees Celsius and leaves at 25 degrees Celsius. Macam ni. Okay, pressure the same, 300 kilopascal in the outlet of the water. Okay, so determine the mass flow rate of the cooling water required. Okay, we have the mass flow rate of the refrigerant 6 kilogram per minute. This one 6 kilogram refrigerant 6 kilogram per minute. You can change it into second. So we want to know mass flow rate cooling water required to cool down the refrigerant water. Okay. Okay, so we are going to use the energy balance for heat exchanger condenser. So macam mana? Boleh tengok, you can look up at the slides. Energy balance for heat exchanger. So heat exchanger, so we neglect kinetic energy, potential energy lah. Since it's not given here velocity or altitude, so we just neglect it. Kinetic energy or potential energy. And then what about power? Okay, so power heat exchanger, the function of the heat exchanger is to exchange heat, so it doesn't produce any power or use any power. Okay. So no power, no power given here, and so we only have apa tu? Q and H enthalpy. Okay, for Q, okay. Yes, we understand that the device is a heat exchanger. Okay, but Q in the energy balance here means that heat transfer or heat inlet or outlet from the device, the heat exchanger to outside or from the outside to inside. So here there are no heat exchange outside the system, inlet inside or outside the system with the environment. Okay, so or the heat transfer is very small, not significant compared to the enthalpy, the energy change within the system, which is the condenser here. So we can neglect the heat transfer since it also is not given here, the heat transfer. So we can neglect the heat exchange of the device with the environment. Means the environment is not included in the closed system that we are going to focus on, going to study. Okay, so we only have in the energy balance of a heat exchanger, we only have enthalpy. Okay, the heat exchange by mass, enthalpy. Okay, just now you are going to locate point 1, point 2, point 3 lah. So we call it this one, point 1, this one 2, this one 3, this one 4. Okay, we just name it 1, 2, 3, 4, so it's easier for us to write down the equation. Kau berapa dah? 37. So in remember the energy balance in equals to in out steady flow. Okay, so inlet. So what is in? Number 1 and number 3 Number 1 dengan number 3 yang in, out, number 2 and number 4. Okay, it's just numbering So we have M1, H1, plus inlet M3H3 equals to M2H2 plus M4 outlet juga. So since we have 2 inlet and 2 outlet, so that's why we have energy balance this way, like this. Okay, M4H4. Okay, inlet refrigerant and the water equals to outlet refrigerant and water. Okay, so just now we have the mass given for refrigerant. So the mass given here for refrigerant 6 kilogram per minute is the total the mass of the refrigerant. So we assume that the mass is from conservation of mass. The mass is being conserved. There are no mass loss. Okay, any mass transfer. Okay, so we have so this is M1 and M2. Mana nak tulis kat sini lah. Okay, so M1 from the conservation of mass is being conserved. So we assume that mass there's no mass loss in terms of mass. So mass inlet and outlet is conserved the same. So this one is the M of the refrigerant. R134 just now, and we have also water. Okay, water, the one that we are going to calculate. Water. So here I present. Okay, so we can factorize, rearrange these equations because M1 equals to M2. So we just put it this way: 134. H2 minus H1 minus H2 minus H2 equals to M4 M3 is the M refrigerant. M4 M3 is the M water. H4 minus H3. Okay. So this is from the energy balance. We have the mass and the enthalpy. So our task now is to search for the enthalpy. Okay, so that we can search for calculate the mass of the water, mass of the refrigerant we have. So we need the mass of the water. So H1, start with H1, H2, H3, H4. Okay, first, of course, we start with the H1. It's okay. H1, H2, H3. Okay, we start with the water lah. Water first. H4, H3. So we use the table for water. So this time I think we can use the table that we already have. Ni water. Given temperature 15 and 24 degrees Celsius, 15 and 24 degrees, 300 kilopascal. This one, table 300 kilopascal, 300 kilopascal. Okay, we can use table A4 for water, liquid. Okay, H, water H in, H3. So H3 300 kilopascal, 15 degrees Celsius. 300 kilopascal, 15 degrees Celsius. 15. 15. So this one 15. So we look at the temperature. We don't look at the saturated pressure because we don't know the saturated pressure at that point of the water. Okay, the water is not at the saturated point. So we just know the temperature 15 degrees Celsius. So 15 degrees Celsius, the water in a fluid is 62.982. And at the exit, 25 degrees Celsius. 25 degrees Celsius, the water still in the water liquid state, okay, is 104.83. Okay, so we choose this one, 15 and 25. 15, 62.982. 25 degrees Celsius outlet of the water is 104.83. Okay, we choose the HF, H liquid. Okay, and okay, so that is for water. For refrigerant, okay, so for refrigerant here, it is refrigerant is to be cooled by water in the condenser. Okay, so refrigerant here is we can assume it as an ideal gas. Okay, but we have to use refrigerant table. Wait, wait sekejap. Saya tukar table. Refrigerant table. Bagi it is table 11 and table 13. I share first. So this one table 13 first. Okay. Okay, so the refrigerant just now is being cooled down by the water. So it started from the hotter, warmer side, warmer temperature, hotter temperature. So we can use this for refrigerant R134A. Okay. Superheated, okay, superheated refrigerant is like the superheated water table, just that this one is for refrigerant R134A. So pressure 1 megapascal and temperature 70 degrees Celsius at the inlet. So 1 megapascal. 1 megapascal is this one. This one. Okay, this one. And temperature 70 degrees Celsius. So we have enthalpy around 303.85. 303.85 kilojoule per kilogram. 70 degrees Celsius. Superheated refrigerant, so superheated vapor. We're going to cool down this superheated vapor. Okay. From a hotter temperature, a warmer temperature, 303.85 enthalpy, P1 megapascal. And at the exit, okay, at the exit we have T for 35 degrees Celsius. So this one we have even value. So we just take a middle, 35 degrees Celsius. 35 degrees Celsius saturated refrigerant. And enthalpy around in the middle, around 100, this one in the middle of 99 and 102. So around 100 for 35 degrees Celsius, around 100. Okay. Okay. If you draw this process in a TS diagram, I do this one. Okay, TS diagram just now. So TS diagram only concern the working fluid, which is here is the refrigerant. Refrigerant is the working fluid of the TS diagram, not the water. Water too is the heat sink, the source of the heat to cool, the source of the cooling to cool down. Okay, so in the TS diagram, we only focus on the refrigerant. So the process just now, if we have the mountain here, okay, superheated, saturated refrigerant, temperature, what is berapa tadi? 103, 100. Okay. Kurang macam ni lah. So this is the condensation process. In the for the refrigerant condensation process from point 1 to point 2, exit inlet outlet. Okay, so just now at the inlet, it is whether it is superheated vapor or it is on the around the saturated vapor line. So that's why just now we use the superheated vapor table for refrigerant. And after being condensed, exchange heat with the cooling water. So cooling water here, imagine we have cooling water here, exchange heat, cooling water. So we expect without any loss, ideal process, we expect that exiting the condensation process, the refrigerant has become a saturated liquid before it continue back in the compression balik. Kan? So kat sini saturated liquid exiting the condenser. So that's why at Z 0.4 we choose the saturated refrigerant table A11. Saturated line, saturated here. Okay. So that's what happened in condensation process. So back to this slide. So we can calculate here M water. So we have H4, H3, H1, H2. Okay. So just calculate M water. You can leave it in kilogram per minute. If you don't want to change this one, you can also leave it in kilogram per minute. And last before we finish, so 1250, last questions, the heat transfer rate from the refrigerant to water. So now we are going to calculate the heat transfer rate, refrigerant to the water. Okay, so heat transfer rate, tulis ni. So heat transfer rate, the definition of heat transfer. So we calculate from the as if the from the water side. So Q water. Now we know the MW from the first questions. So water just now H4, H3 minus H3. Okay, so you have your Q heat transfer rate of the process, refrigerant and water. Okay, check. This one. So this one is actually Q. Q. So either you want to use this one or you also want to use it. Mana-mana nak calculate guna refrigerant side or water side also can, because we assume that the energy balance, the energy is balanced, it totally no pressure loss. Ideal case, so the total heat produced or by the water is being given to the refrigerant. So it's the same from both sides. So we can use this part or you want to use this part also can. Case we calculate the Q, heat transfer. Okay, that's all. That's all for tutorial. Any questions from you guys? Any question from you guys? Understand or not? So we have seen three process of steady flow device. Normally we will assume steady flow. Jarang lah we use unsteady. So we've seen the first one, turbine expansion process, and then compressor compression process, and this one condenser condensation process. So those three, turbine, compressor, condensation, are part of a gas turbine, basic gas turbine cycle. Okay, so basic gas turbine cycle, repeat, we have compressor and then evaporation or combustion chamber, and then we have expansion turbine, and then we have condensation for closed gas turbine cycle. But for aircraft engine, it is open cycle, so we don't have condenser. Condenser ni untuk power plant je. For aircraft engine, we don't use condenser. Okay, okay. Any question? Okay semua? Everyone okay? Understand? Umi okay?
No questions actually.
Said?
Okay, good, Doctor.
Okay. Okay, kalau tak ada apa-apa, so we nothing else, we stop here. Okay, we stop recording. Okay.